In this example, we're asked to set up and evaluate an iterated integral for the double integral over the region D of y times dA, where D is bounded by the line y equals to x minus 2 and the parabola x equals to y to the square. So let's sketch the region D. And we see here that the region D is bounded by the line y equals to x minus 2 and the parabola x equals to y to the square. The first thing that we need to do is we need to find the intersection points between the two curves. So solving for x, the equation y equals to x minus 2 will give us that x equals to y plus 2. And we also have the parabola y x equals to y to the square. So equalizing these two will give us that y to the square is equal to y plus 2. And that gives us that y to the square minus y minus 2 equals to 0, which means if we factor that we have y minus 2 times y plus 1 equals to 0. And that gives us two roots, y equals to 2 and y equals to negative 1. So setting y equals to 2 and y equals to negative 1 to either one of the two curves that we have will give us the two intersection points, the point 1, negative 1 and the point 4, 2. And these are the points on the graph. The point 4, 2 is up here and the point 1, negative 1 is down there. If we describe the region D as a type 1 region, then the upper boundary curve will be y equals to square root of x, but the lower boundary curve consists of two parts, y equals to negative square root of x for x between 0 and 1, with 0 and 1 included, and y equals to x minus 2 for x between 1 and 4 with 1 and 4 included. So that means that we'll need to set up two integrals and take their sum, but we can also describe the region D as a type 2 region. And in this case, we'll have a left boundary x equals to y to the square and a right boundary x equals to y plus 2. And this all happens while negative 1 is less or equal to y, and this is less or equal to 2. So we have the region D, that is the set of all points x, y, such that negative 1 is less or equal to y, less or equal to 2. And x is between the two curves y squared and y plus 2. So y squared is less or equal to x, and this is less or equal to y plus 2. So setting up the double integral will give us the double integral over the region D of y times dA. And this is equal to the type 2 integral from negative 1 up to 2, and from the integral from y squared up to y plus 2 of y times dx dy. And this is equal to the integral from negative 1 up to 2. And now we can evaluate the integral of y times dx, which would give us x times y. And that needs to be evaluated between x equals to y to the square and x equals to y plus 2 times dy. That will give us the integral from negative 1 up to 2. And we now can pull y outside, and we need to evaluate x between x equals to y plus 2 and x equals to y to the square. So that will give us, for x equals to y plus 2, we'll have y plus 2, and then minus y to the square times dy. So that will give us, if you distribute y, we'll have the integral from -1 up to 2 of y squared plus 2y and then minus y to the third times dy. And that will give us integral of y to the squared dy is equal to 1/3 y to the third. And then we have plus 2 y to the square over 2 will give us a y to the square. And then we'll have minus 1/4 y to the fourth. And we need to evaluate that between y equals to -1 and y equals to 2. So that will give us 8/3 plus 4 minus 1/4 times 16 for y equals to 2. And then we have for y equals to -1, we'll have minus 1/3 and then plus 1 minus 1/4. So this is equal, from the first parenthesis, we'll have 4 with minus 1/4 times 16. So this is 4 minus 4, so that is equal to 0. So we have just 8/3, and then we have plus 1/3, and then minus 1, and then plus 1/4. So that will give us 8/3 plus 1/3 is 9/3. So this is equal to 3 minus 1 is 2, plus 1/4 will give us 9/4.